Well, hello. Today we'll talk about reflection transformations, or just reflections. First thing I did was make a big mess here on the page. These are various reflections of image A. Here's the main one here. The others are images. Maybe I should have put them in a different color. Too late now. These are reflected about the y-axis, the x-axis, the line y equals x, and the line y equals minus x. It's these two lines here, of course. What are our rules for a reflection? Well, we looked at these earlier. This is almost just a review. Well, we have some rules right there. Reflected about the x-axis. The x-coordinate stays the same, but the y-coordinate becomes negative, and that's what we did here. Minus 4, 1 becomes minus 4, minus 1. Minus 6, 1 is minus 6, minus 1. And up here we had minus 5, minus 3. And down at the bottom, minus 5, minus 3. It all makes sense. Notice that, just like you'd expect, when you look at the reflection of, say, a hillside in a lake or a bridge, everything is flipped, isn't it? Well, same thing here. This point goes to here, this point is here, and if you were to flip A vertically, you would end up with this. What about the y-axis? Well, again, that's pretty easy. Everything stays the same. You just make the x-coordinate negative. So we've got minus 4, 1 becomes 4, because the negative of a negative is just negative. Same thing here. Minus 6, 1 becomes 6 minus 1, and minus 5, 3 becomes 5, 3. So here's about the y-axis. This is about the x-axis. Notice that we flipped it vertically here. This would be a horizontal flip if you could tell one side from the other, because notice this side over here became this side here. So if this were a different color, you'd see over here. Since this is an isosceles triangle, flipping it horizontally doesn't have any visible effect, does it? But if I change the color here, now we see that things have in fact flipped horizontally, just like down here it flipped vertically. If this thing was lying on its side with the long end over here, then it would be lying at its side with the long end over here, not here. In other words, if it was on the left over here, the long end would be on the right over here. Just as the top of our image becomes the bottom of our reflected image when we're reflecting about the x-axis. Now the left becomes the right when we're reflecting about the y-axis. And it's not quite that simple when we reflect about other lines. For instance, the line x equals y. And I just about ran out of grid room here. What's our rule? For the line y equals x, we just reverse a and b. So minus 4, 1 becomes 1 minus 4. That's right here. Minus 5, 3 becomes 3 minus 5. That's right here. And minus 6, 1 becomes 1 minus 6, and that's down here just off the grid. Notice this reflection again. Well, it didn't flip it horizontally and it didn't flip it vertically, but it sure looks like it was the same. The actual object got rotated 90 degrees. This is not a rotation transformation, but when we flip everything, this point goes to here, this point goes here, and this point goes here, and the result is that this whole object ends up getting rotated 90 degrees. You think something like that will happen when we flip about the line y equals minus x? Well, you'd be right. Up here, it just flipped the other way, didn't it? Here it rotated, it's as if it rotated 90 degrees. We'll say to the right or clockwise. This one rotated 90 degrees counterclockwise, or to the left, you might say. But they're not rotation transformations. That's just what happens when you reflect things. Just as this is not strictly a flip transformation, it's a reflection, but it does invert it in the vertical sense. This reflecting across the y-axis flips it horizontally, and across y equals x or y equals minus x, that produces a 90 degree change. And notice that these triangles, if we were to inspect them, would all have the same perimeter, the same area, and in fact, they would all be congruent. So this is called an isometry. These reflections are called isometry transformations, or just plain isometries, or congruent transformations, or congruence transformations. They're also called rigid motions. The word rigid is pretty graphic. It means that the object itself does not get changed. Probably should have mentioned it during the section on translations, but one of the best reasons for studying transformations at all isn't just moving geometric objects around, well, moving them anyway, and then seeing what happens to them after you move them. For instance, with these congruence transformations, they've changed position, and they may have changed orientation, at least from our point of view, but other than that, they haven't changed. When I say orientation from our point of view, well, you can flip something vertically and it's changed orientation. Unless, of course, you turn yourself upside down. If you stand on your head, it doesn't look like the orientation has been changed, does it? That's because things like that are relative. So, suppose you had some land, a piece of land, say, and you're going to survey it, and it's, land doesn't have very regular shapes to it. So you've got this thing here. Kind of looks more like a state than a piece of land, but oh well. Now you're going to survey it, and say this part here might be a river. You not only need to know the boundaries, but where the boundaries are, and maybe you've got a really huge tree right there that's almost historical significance. And then you might have, say, a pond or something in here. One of the things you could do, and surveyors do this, is to lay out a grid system. For instance, you could put your origin right here. And then everything on the property. Gee whiz. So when you're doing this, you lay out your own little grid system here, and you can plot exactly where everything on your land is. No problem. Using this, you can also compute the total area, the acreage. You could determine how many linear feet your property bounds this river here. How many linear feet follow the river. What's it called? Frontage property, I think. Not real big on real estate, sorry. When you do all this, you've used this grid system here. Well, we already showed that when you translate things, it doesn't matter. The shape, the perimeter, everything else is a congruence. So if we were to take this piece of land and pick it up and move it all at once somewhere else, that would be a translation. Suppose we didn't move the land. Suppose we just moved the coordinate system. Wouldn't that be about the same thing? For instance, here, if we used like a really coarse grid system, 1, 2, 3, this would be like the point 30 over here. Well, on a new grid system, just like with a translation, this point may have an entirely different coordinate, 2 entirely different coordinates. But it'll still be, and every one of these points will have a different coordinate, but it's still the same shape, it's still the same area, same perimeter, everything stays the same. We know that from our principles of translations and any congruent transformation. So instead of moving the object, wonder what happens. The thing about me setting up my own little grid here is that I'm not the only person concerned with this property. Suppose this property is in a county. Well, the county has their own way of laying out their entire county, and this little piece of property is just one little plat, or part of a plat, in a county map. You've created your own little map of your property with an origin here and your own set of XY axes, and you've laid out a grid. The county has another grid system. And while this was the point, say 30 on your grid system, this may be the point 125.89 on their grid system. Their system, rather than take the whole land and move it off to the right and up, if their origin is down here, what we've done is taken our coordinate system and moved it to the left and down. And it's exactly the same thing. Remember? Well, maybe you don't remember. If you're hearing it for the first time, motion is relative. It doesn't matter whether... Well, motion is relative. You always have to define it relative to something. For instance, when you're traveling on the Earth's surface, your motion is relative to the Earth. You're doing 30 miles an hour relative to the Earth. How fast you're going relative to the Sun or the Moon or Mars, well, that's an entirely separate question. It's pretty hard to know. It would take a lot of mathematics to figure out your speed relative to those other objects, but relative to the Earth's surface, you can compute that. Well, it's the same thing. This has coordinates relative to your grid system. It also has coordinates relative to someone else's grid system. In this case, say we're talking about the county. They have their own. But our transformation theorems tell us that when we move the coordinate axes, in other words, move our origin from here to miles away, we might have gone 10 miles west and 3 miles south, and then set up a whole new coordinate system. Our perimeter will be exactly the same, our area will be the same, the distance from our tree to any boundary will be the same, the size of our pond will be identical. Nothing will change when we change grid systems other than the coordinates. And they all change together. So we change the numbers. This, as I said, this might go from 30 to 125.89, but every other point in here would change exactly the same way, which means it doesn't matter whether we use our coordinate system or the county's coordinate system. The state may have another coordinate system. They might set 0 someplace completely different from where the county does. And this could also be within some city limits, and they would have their own grid system. And that's the beauty of it. It doesn't matter which coordinate system you use, you get the same answers always. And that's what these transformation theorems are telling us. And that's why they're worth looking at. In fact, transformations of functions and transformation of coordinate systems are generally much more useful than actually transforming the geometric objects. So what about these reflection transformations? How does that fit this idea that transforming the coordinates is usually more useful than actually moving geometric objects around? Because our theorems tell us that if we transform the coordinates, it's the same as transforming the object. So what does that mean in a reflection? How do we transform a coordinate system in a sense of a reflection? Well, that'd be like flipping this thing vertically, wouldn't it? In other words, we get -1, -2, -3, -4. The negative numbers would go up, and the positive numbers would go down. Pardon me. If that sounds totally ridiculous, keep in mind the temperature. I think it was the Celsius. The man who developed that did not develop it to go upward from 0, and then I think boiling point is 100 degrees. He put the boiling point at -100. In other words, his scale was negative. He just reversed it. Electronics, it turns out to be fairly arbitrary, what you call positive and what you call negative. You just have to keep it the same. Once you've decided that something is the positive terminal, that polarity has to be positive always. You can't go back and forth and say that one polarity is positive one day and then next week say, oh no, we're going to call that polarity negative now. No, once you pick the convention, you have to stick with it. A long time ago, positive terminal for electricity was actually named incorrectly, you could say. It really should be the negative terminal, but it really doesn't matter, because when you switch, when you invert systems, you can go up to down or down to up. One's more intuitive than the other. One seems to make more sense, but they don't really change the outcomes. So what does that mean here? Well, for instance, not sure I had the triangle in the right spot. At any rate, what I'm going to do is leave the triangle, the geometric object, right where it is, and flip the coordinates. If I flip the coordinates, I hope you can read upside down. Here's -1, -2, 3, and 4. X coordinates are all still the same. They're upside down, but you can see that we still have the positive numbers here and the negative numbers here. So our new coordinates for this one are -2, -1, -4, -1, and -3, -3. What were the coordinates when we flipped the object and left the coordinate system the same? Well, over here, when I reflected the triangle itself and not the coordinates, what did I get? Exactly the same thing. -4, -1. Exactly the coordinates we just looked at. See, just like that. We can flip the coordinates, and we can do that with all of our transformations. At least our congruence transformations. We can do it to the coordinates instead of doing it to the original object. I can shift this object around and reflect it, or I can shift the coordinates around. I can reflect the coordinates, and later on we'll learn about rotating the object or rotating the coordinates. But that's, I think, the most important part about these transformations, and showing that they don't really change the object, because it shows that most of the things we study in geometry are what's called coordinate invariant. And it makes sense that they would be coordinate invariant, because most of this stuff was developed by the ancient Greeks, and they didn't have coordinates. If you showed them a coordinate system, they wouldn't know what you were talking about. This system we use here, our coordinate system, it's called a Cartesian coordinate system for a reason. It was developed by a French guy named Descartes, and somewhere in the Renaissance. So we're talking 1800 years after the Greeks were developing geometry. So they certainly did not have any theorems or formulas which would have been coordinate dependent, because they didn't have coordinates. So all the things we're going to study later on that allow us to compute areas, volumes, surface areas, they're all going to be coordinate independent. And that's another way of saying that under congruence transformations, those properties don't change, such as you could say area is an invariant under a congruent transformation. The perimeter is an invariant under coordinate transformations. Pardon me. Yeah, under congruent coordinate transformations. Yeah, now we can work a few problems. Reflection transformations are actually fairly easy, unless you try to reflect across a curve or something weird, but we're not going to do that. In this one, they ask us to reflect across the line x, gee whiz, x equals minus 1. That's this line right here. Well, when we were reflecting, say, across the y-axis, it was easy, because we just had to change the sign of the x-coordinate. If this was minus 1, it became plus 1. If it was 2, it became minus 2. Well, when you've got a line that's not one of the axes, it's not that much different. For instance, this point. Oh, another thing we got to take a look at, since this is a vertical line, our y component in all these points is not going to change. Only the x coordinate. Now this is 2 units from this line, right? So all we have to do is go 2 units the other way. What point is that? That's 1 minus 2. And we're not reflecting about the y-axis anymore, it's this one. So we're 2 units to the left, now we have to go 2 units to the right. Same thing here. We're 4 units to the left of this line right here, so we have to go 4 units to the left. That puts us right here. And that is the point 3 minus 1. And our next point here, well, looks like we're 5 units to the left of this line, so we have to go 5 units to the right, which I think puts us right here. The y-coordinate stays the same. So we've got 4 minus 4. So when we have our new vertices, we connect them, get our new triangle. And here's C prime, B prime, and A prime. You can see where the reflected points went to. That's all you had to do. It's really very easy reflecting about vertical or horizontal lines. And here they're asking us to figure out what the line of reflection is. We've got our pre-image here and our image. For instance, here we have the point 0, 1. You can just put that in there. 0, 1. And that goes to the point 1, 0. Now this is where it probably pays to take a look at our coordinate rules for some standard reflections. What did we do here? Looks like we just reversed the x and y coordinates, right? So which one of these would correspond to a reversal? Well, that one looks like we just switched them, and that's the line y equals x. And that actually makes a lot of sense, doesn't it? If we sketch that in there, doesn't this look like a reflection? Doesn't this look like a reflection of that, about that line? Looks that way to me. So the actual is y equals x right there. D would be the correct answer. Well, as I said earlier, one of the most important applications of transformations is transforming functions. And here they ask us to do exactly that. First we graph 2x squared minus 5. That's the red line here. Notice this, the y-intercept is minus 5, which is what you'd expect when x is 0, y is minus 5. Now what's the reflection about the x-axis? Well, remember, it's for any point AB, it's a minus b. In other words, the x-coordinate doesn't change, but the y-coordinate just becomes negative. So our low point, our minimum for the original equation, becomes our maximum for the reflected equation. The point 0 minus 5 becomes 0, 5. And this illustrates it right here. This looks like 1.50, and that goes to 1.50 because the negative of 0 is just 0. And they have exactly the same value when they cross the x-axis, which makes perfect sense. So here's the new one. And what would the equation of that be? Well, that's kind of easy. All we have to do is, if we make the y-coordinate negative, all we're doing is just taking the negative of the entire thing, that is to say the whole equation, or we could write this as, oh, that's y, say. But that's the same as writing 2 minus 2x squared plus 5. So this here, transformed equation, that's the blue line, and the original is the red line. Notice that to reflect about the x-axis, all we had to do was take the negative of y. Well, that's about it.